Welcome to our video on chemical reaction engineering. Now in this video, we'll be looking at how to determine kinetic parameters. And then before we can understand the kinetic parameters, there are a few definitions we have to know in order to help us understand the course. So our first one, we'll be looking at homogeneous reactions. Now when we say homogeneous reactions, it's first a reaction that involves only a single phase. So when a single phase, I mean that the reactant and the product are in the same phase. So when you have a reaction like A plus B going into C and they are all in the gaseous phase, then we say that this reaction is homogeneous reaction because both the reactant and then the product are all in the gaseous phase. So a practical example would be the Bosch-Haber process. Right? So we have ammonia, which is in the gaseous state, plus hydrogen in the gaseous state, forming ammonia in the gaseous state. Right? So we can have something like this. Yes. Now because the reactant and then the product are all in the gaseous state, then we can see that this is homogeneous reaction. The next one is heterogeneous reactions. Now with the heterogeneous reaction, it's just the exact opposite of the homogeneous reaction. It involves more than one phase. So it means that the reaction involves more than one phase. So it can be that either the reactant and then the product are in different phases, or even the reactants are in different phases. Right? So we can have A in the gaseous state plus B in the liquid state, forming, let's say, C in a different state, let's say liquid or gaseous, any of them. Now because the phases are different, then we say that this is a heterogeneous reaction. So example, we can have the combustion of heptane, so C7H16 plus oxygen going into 7CO2 plus 8H2O. So we can have 11 here, right? Now we know that heptane, because it's a higher hydrocarbon, it's in the liquid state, and then the oxygen is in the gaseous state, and then we are forming this can be the gaseous or in the liquid state. Now the heptane is in a different phase as the oxygen, right? Then we can see that the reaction is heterogeneous reaction. Then our next definition will be irreversible reactions. So irreversible reactions, they are reactions that proceed in only one direction, right? Only one direction. So we have A forming B, and now they proceed in one direction till the reactant is fully consumed, right? So when you have A forming B, and now you have like 20 kilograms of A at startup, right? Now the moment all the 20 kilograms of A gets used up, then the reaction stops, and the reaction proceeds in only one direction, that is in the forward direction. Then we see that this reaction is an irreversible reaction. And then we have reversible reactions too. Reversible reactions. Now the reversible reaction is also the opposite of the irreversible reaction. It's a reaction that proceeds in two directions or more than one direction. So proceeds in two directions. Now reactions can only proceed, the maximum is in two directions, right? So it's either in the forward direction or in the backward direction. But then with the irreversible reaction, both occur at the same time, right? So we can have A going reversibly to B. So in this case, A is forming B, and at the same time B is also producing A. Now on the way the reaction occurs, this is how it occurs. So let's say we are starting and then we have like 50 kilograms of A. So now when more of the A forms B, and now the B becomes in higher concentration than the A. Now the B tends to form A. So the reaction will proceed in both directions until equilibrium is established. And when the equilibrium is established, it means that the amount of A and then the amount of B. So the concentration of A and the concentration of B are the same. Right? So when they are the same, then the reaction stops. Right? But then for the irreversible reaction, the reaction stops when the reactants are consumed fully. And then for the reversible reaction, the reaction stops when equilibrium is reached or when equilibrium is established. That's when the concentration of the reactant and then the product are the same. And also we can look at rate of reaction. Now rate of reaction determines how fast the reaction occurs. So you have these two things you have to look at. So the thermodynamics of a reaction and then the rate of a reaction. Now in the thermodynamics, it determines how feasible the reaction is. So the thermodynamics will just tell us whether the reaction can occur or not, and that is based on the Gibbs free energy change. Right? So when it's less than zero, that means the reaction is feasible or is spontaneous. When it's greater than zero, it means the reaction is not feasible or it's not spontaneous. So then we have to use a different form of energy to make the reaction occur, whether electrical energy or any other form of energy. But then the rate determines how fast the reaction is being occurred. So the how fast is based on how fast the reactants are being consumed to form the product or how fast the products are being formed. And the last thing we are going to look at is the order of a reaction. Now the order of a reaction is from experimental data, right? So when we write our rate equation, our rate equation K CA, so let's say CA is our concentration of the reactant, exponent N, right? Now this N here is our order of the reaction, right? And then we can determine that based on experimental values. Now, so when you talk about kinetics, so kinetics is related to the rate, right? So the kinetics is about the rate of the reaction. So kinetics, how fast something is being occurred. And the rate is also how fast, right? And now the video is more centered on determining the kinetic properties, right? So if the kinetic depends on the rate, then we have to go back to our rate equation and see that. So first of all, you should know how to write rate equation. So writing rate equation. When you have any reaction taking place, so let's say A forming B, you write the rate equation based on the reactant. Sometimes you can also write it based on the product. However, the rates will still be the same, but then one will be the negative of the other. So if you are writing in the form of the reactant, because the reactants are being consumed, that means the rate will be a negative, right? So amount of A being consumed, the amount of A disappearing. And then when you are writing in terms of the product, it's supposed to be positive, right? Because B is being produced or B is being formed. However, the rate will still be the same. So if the rate based on the reactants, you are getting negative 20, let's say kilomole per second. Then based on the product, you are going to get 20 kilomoles per second. So it means that if 20 kilomoles of A is being consumed per second, and then 20 kilomoles of B is being produced per second. Yes. So in terms of, but in this video will be much centered on writing it in terms of the reactant. Now in terms of the reactant, we write Ra is equal to negative KCA. Now we are putting a negative here because if we are writing in terms of the reactant, then the rate should be negative, right? And then when I write it in terms of the product, so in terms of the product is B, right? So RB should be equal to KCB, right? And then supposed to be positive for product. Now, because RA and RB are the same in terms of magnitude, then we are going to see that RB will be equal to negative RA, right? And then our rate should be negative when writing in terms of reactant. So mostly we write it as negative RA. The moment we bring the negative RA here, then our KCA now becomes positive, and then we just write KCA because RA is negative KCA. We can multiply it by negative, and then we get this. But then I'm going to use this to represent our rate in terms of reactant, right? So we have negative RA equals KCA. When you want to write the same rate in terms of the product, it's going to be negative KCB. Why? It's because we are equating the rate of the reactant to that of the product here. So we just have to negate that, so that in actual sense I'm going to get negative RA being equal to negative KCB. And then this cancels this, and then we get our rate. Sorry, if this is our rate, then we get our rate in terms to be positive as we want. Right. So we are looking at kinetic parameters. So now kinetic parameters, we are going to focus on the rate constant. So in our next video, we'll look at the order. But for now, we'll be looking at the rate constant. Now, for the rate constant, so rate constant. So now the K here, the K that we have here. So from the rate equation, R is equal to KCA. Negative R is equal to KCA. This K here, even though we are calling the K as a rate constant, it's not entirely a constant. Why? Because it depends on temperature, right? So the relation between the rate constant and the temperature is given by the Arrhenius equation. And the equation which is given by K is equal to A exponential negative EA over RT. Our K here is our rate constant. This A here is our pre-exponential factor or frequency factor. And then this EA here, so it's E subscript A, is what you call activation energy. And then our R here is our gas constant, T here is our temperature. We know that before any reaction occurs, there should be a minimum amount of energy that the reactant should overcome before the product can be formed. That's why even in some reactions, you have to increase the temperature before the reaction occurs, because you're increasing the temperature to increase the energy, right, of the reactant so that they can exceed the minimum amount of energy. This minimum amount of energy we always talk about is what we call the activation energy. Now, the activation energy refers to the minimum amount of energy needed to be overcome by the reactant for product to be formed. And this pre-exponential factor, right? So when you have our graph like this, and then we have our reactant wanting to form product, there is an amount of energy that the reactant should overcome, right? So I'm representing this as the energy. So this activation energy. Now, the amount of times the reactant try to overcome this activation energy is what we call the pre-exponential factor. Right? So the amount of times the reactant try to overcome this activation energy is what we call the pre-exponential factor. And then with this exponential term, with the whole of the exponential term, refers to the probability that the reactant will be able to overcome this activation energy. And because this is a probability, it can't exceed 1, right? So it's always be less than 1. So our whole term here is the probability that indeed the reactant can be able to overcome the product. So it can be able to overcome the activation energy for product to be formed. Now, so now that we know the Arrhenius equation, K being equal to A exponential negative EA over RT. We can perform a series of experiments. We can determine the activation energy based on experiment values. We can perform a different experiment. So we are going to vary the temperature and then the rate constant. Because the rate constant depends on temperature, when we vary the temperature, we are going to get rate constant for each reaction, right? Sorry, for each um experiment that we do. So when we do that, we can get temperature and then K values. And then based on this, we can be able to get our activation energy of that particular reaction. So we have to model this equation into the linearized form, which is y is equal to mx plus c, right? Now, to linearize this, k is equal to a exponential negative ea over rt. We want to linearize this. So we first have to apply ln to both sides. So we get ln k is equal to ln of the whole expression here. So ln k is equal to ln a plus. So we know that in the guiding, when we are multiplying, it means that they were adding, right? So ln a plus ln exponential negative ea over rt. Then we can get ln k being equal to ln a minus ea over rt. Right? Because ln is the inverse of exponential. So when they meet, they cancel out, and you're left with the exponential term. So let's arrange it well. So we get ln k being equal to negative ea over r multiplying 1 over t plus ln a. And then this is equal to our y equals mx plus c. So now our y here is our ln k, our x here is 1 over t, and our c here is ln a. So our c here is our intercept, m is our slope. So m is also equal to negative ea over r, right? So when you plot the graph of y, which is ln k, against your x, which is 1 over t, because the slope here is negative, so the graph will always be something like this. And then when you find your slope will be equal to negative ea over r, right? And then when you evaluate this, you can get your activation energy, right? So we can try one example here. So let's assume that we have a reaction, which is a first order reaction. You have a reaction which is a first order reaction, and then from experiment, we've gotten temperature against, so our temperature is in degrees Celsius with rate constant in R, right? So per R, because we are assuming it's a first order reaction, so per R. And then at a certain temperature, so let's say 38.5, we have a rate constant of 0.044, and at 53.1, you have the rate constant to be 0.301. Because the rate constant depends on temperature, so anytime you vary the temperature, the rate constant will also be varied. And then 77.9, we have 1.665. Now we are supposed to find the activation energy and the pre-exponential factor. So find EA and then the A here. So because you have the equation in the linearized form, right, you just have to go back to it. Ln k is equal to negative ea over r 1 over t plus ln a. So we are going to plot y values, which will be ln k, right, against x values, which is 1 over t. Now before we do that, our T here supposed to be in Kelvin, not in degree Celsius. So we can extend this and then we can convert the degree Celsius into Kelvin. And you know how to convert degree Celsius into Kelvin. So temperature in Kelvin will be equal to 273 plus that in degree Celsius. So for the first one, 38.5, we get 38.5 plus 273. 38.5 plus 273, and then we get 311.5. And then the next one, 53.1 plus 273. 3.1, we get 326.1, and then 77.9 plus 273, get 350.9. So they are all in Kelvin. Our y here is ln k, so we just have to point ln of this. So ln for the first part, ln 0.044, that will give us minus 3.124. Ln 0.301, that will give us negative 1.2. Right, so 01. And then ln 1.665, so 0.51. Then we come to the x, 1 over t. So 1 over 311.5, 0.0032, 1 over 326.1, then we get 0.00307, then 1 over 350.9, we get 0.00285. So when you plot this against this, so these values against these values, so let's see if these are 0, our y extends to the negative. So let's say negative 1, negative 2, negative 3, and then we have 1 here. So here becomes 0.5. And then for the x part, you can have 1, 2, 3. So all times 10 exponent. So we move 1, 2, 3, and then 10 to the minus 3. So negative 3.124 with, so when you convert this to 10 to the negative 3, it becomes 3.2. So we are going to get something around this point. And then for the second part, negative 1.201, 3.07. So somewhere here. And then the last one, 0.5, and then 2.85. Somewhere here. Right. We are going to get something like this. Right. And then we can find our slope. We are going to find our slope. Then we can see that our slope that we plotted would be equal to negative EA over R, because this term is our slope. So our EA becomes negative R times the slope. And then R is your gas constant, which is 8.314 kilojoules per kilomole Kelvin. Right. So your EA becomes negative 8.314 times your slope. Right. However, you can point this in your calculator, right, to get your slope directly, then you intercept. And then our intercept, which we get, our intercept is where the line cuts the y-axis. So where it cuts should be equal to ln A then our A becomes exponential of the intercept. We have a way of punching this into your calculator for you to get your slope and then your intercept. So try your best to find out.